Corrosion fatigue damage mechanisms as a part of environment-assisted cracking. Description of corrosion fatigue damage mechanisms based on API 571, a form of fatigue cracking in which cracks develop under the combined effects of cyclic loading and corrosion. Cracking often initiates at a stress concentration such as a pit in the surface. Cracking can initiate at multiple sites. Here's a detailed description of corrosion fatigue damage. Definition: corrosion fatigue is a failure mechanism that occurs when a material subjected to cyclic loading, repeated stress or strain, simultaneously experiences corrosive environmental conditions. The combined effect accelerates crack initiation and propagation, leading to premature failure of the material compared to corrosion or fatigue alone. Here a comprehensive explanation of corrosion fatigue damage. Number 1 is, fundamental concepts. Fatigue is the progressive and localized structural damage that occurs when a material is subjected to cyclic stresses below its ultimate tensile strength. It involves crack initiation, often at stress concentrators, and crack growth with each load cycle until final fracture. Corrosion involves the chemical or electrochemical deterioration of materials due to environmental interactions, leading to material loss, pitting, or weakening. Corrosion fatigue is an synergistic process where cyclic stress and corrosive environment interact to accelerate material degradation, results in reduced fatigue life and increased likelihood of sudden failure. Number 2 is, mechanisms of corrosion fatigue damage. Number A, crack initiation, typically occurs at surface flaws, inclusions, or areas of stress concentration. Corrosive environment exacerbates crack initiation by promoting localized attack, pitting, crevice corrosion, weakening the material's surface layer. Cyclic stresses tend to propagate these flaws into microcracks. Number B, crack propagation. Once initiated, cracks grow under cyclic loading. Corrosion facilitates crack growth by removing protective oxide layers, creating microvoids at crack tips, enhancing stress concentration at the crack tip via localized corrosion pits. Number C, synergistic effect. The presence of corrosion reduces the stress threshold required for crack growth. Cyclic stresses accelerate corrosion processes, and corrosion accelerates fatigue crack growth, creating a feedback loop. There are some factors influencing corrosion fatigue. Factor number 1 is environment. Its effect is presence of chlorides, acids, or other aggressive agents intensifies damage. Factor number 2 is stress range. Its effect is higher cyclic stress amplitudes accelerate crack growth. Factor number 3 is frequency of loading. Its effect is lower frequencies allow more corrosion to occur per cycle, increasing damage. Factor number 4 is material type. Its effect is some materials, for example, high-strength steels, aluminum alloys, are more susceptible. Factor number 5 is surface conditions. Its effect is rough or poorly coated surfaces foster localized corrosion and crack initiation. And factor number 6 is temperature. Its effect is elevated temperatures can accelerate corrosion reactions and fatigue processes. Number 4 is types of corrosion fatigue. Uniform corrosion fatigue occurs uniformly over the surface, leading to general thinning. Localized corrosion fatigue initiates at localized sites such as pits or crevices, often more damaging due to stress concentration. Pitting corrosion fatigue. Cyclic stress accelerates pit growth, which acts as a crack initiation site. Intergranular corrosion fatigue. Cracks propagate along grain boundaries, especially in susceptible alloys. Number 5 is damage characteristics. Crack initiation sites, often at surface flaws, corrosion pits, or inclusions. Crack growth, accelerated at corrosion sites, often with irregular or scalloped fracture surfaces. Fracture surface features, beach marks, indicate incremental growth under cyclic loading. Corrosion products, presence of rust or corrosion deposits on fracture surfaces. Intergranular features, in some alloys, cracks propagate along grain boundaries. Number 6 is detection and analysis using visual inspection, surface corrosion features and crack indication, microscopy, SEM to observe crack morphology and corrosion features at high magnification. Detection and analysis using non-destructive testing, ultrasonic testing, eddy current testing, and detection and analysis using fractography, analysis of fracture surfaces to distinguish between fatigue, corrosion, and combined damage modes. Corrosion fatigue is a synergistic failure mechanism involving the interaction of cyclic mechanical stresses and corrosive environments that accelerate crack initiation and growth, often leading to premature failure. It is characterized by surface or subsurface cracks, corrosion pits, and scallop fracture surfaces, with damage severity depending on environmental conditions, material properties, and loading parameters. Corrosion fatigue based on API 571 affected all metals and alloys. Here's a detailed explanation of materials affected by corrosion fatigue damage. Overview: corrosion fatigue can affect a wide range of materials, especially those used in environments where cyclic loading and corrosive agents coexist. The susceptibility and extent of damage depend on the material's composition, microstructure, surface condition, and environmental exposure. Materials affected by corrosion fatigue damage includes: number 1 is metals and alloys susceptible to corrosion fatigue. Number A, steels. Includes: the first is carbon steels, commonly used structurally, susceptible to pitting and cracking in chloride environments. High-strength steels are particularly vulnerable due to their high residual stresses and microstructural features. The second is alloy steels, contain alloying elements, Cr, Ni, Mo, that can improve corrosion resistance but may still suffer in aggressive environments. The second part of steels is alloy steels, contain alloying elements, Cr, Ni, Mo, that can improve corrosion resistance but may still suffer in aggressive environments. The second part of steels is stainless steels, generally resistant to corrosion but susceptible to chloride-induced pitting and crevice corrosion, which can initiate fatigue cracks. Types such as 304, 316, and 321 are commonly affected. Metals and alloys susceptible to corrosion fatigue. Number B is aluminum alloys, widely used in aerospace, marine, and transportation, susceptible to pitting and intergranular corrosion, especially in chloride-rich environments. Fatigue life significantly reduced when corrosion pits act as crack initiation sites. Metals and alloys susceptible to corrosion fatigue. Number C is titanium alloys, known for excellent strength-to-weight ratio and corrosion resistance, still vulnerable in highly aggressive environments, especially if surface damage or microstructural defects exist. Pitting and localized corrosion can lead to fatigue failure. Metals and alloys susceptible to corrosion fatigue. Number D is nickel and nickel-based alloys, used in chemical processing, aerospace, and marine applications, can develop localized corrosion in aggressive environments, leading to fatigue cracks. Metals and alloys susceptible to corrosion fatigue. Number E is superalloys, such as Inconel, Hastelloy, used in high-temperature, corrosive environments. Susceptible to corrosion fatigue when exposed to cyclic stresses at elevated temperatures. Number 2 of materials affected by corrosion fatigue damage is nonferrous metals and alloys, includes: number A, copper and copper alloys, bronze, brass, prone to disinsification and other forms of localized corrosion. Under cyclic loading, microcracking can occur at corrosion sites. Number A, magnesium alloys, very susceptible to corrosion, especially in chloride environments. Fatigue life is severely compromised due to rapid crack initiation at corrosion sites. Number 3 of materials affected by corrosion fatigue damage is composite materials and coatings. Fiber-reinforced composites can suffer from environmental degradation at interfaces, leading to delamination and crack growth under cyclic loads. Protective coatings, such as paints, platings, can break down, exposing underlying materials to corrosion and fatigue. Factors influencing material susceptibility. Factor number 1 is microstructure. Material would be impacted and susceptible to grain size, inclusions, phase distribution influence crack initiation and propagation. Fine-grained microstructures generally improve fatigue resistance but may be more susceptible to localized corrosion if microstructural inhomogeneities exist. Factor number 2 is alloy composition. Material would be impacted and susceptible to elements like Cr, Ni, Mo enhance corrosion resistance but may introduce microstructural features that influence fatigue crack growth. Factor number 3 is surface condition. Would be impacted and susceptible to rough or damaged surfaces harbor corrosion. Pits that serve as crack initiation points. Factor number 4 is, residual stresses would be impacted and susceptible to welding, machining, or forming processes induce residual stresses that promote crack initiation in corrosive environments. Examples of materials commonly affected. Material type number 1 is, carbon and low-alloy steels, typically applied to pipelines and structural components, susceptible to be damaged such as pitting, pitting-induced cracking in chloride environments. Material type number 2 is, stainless steels, typically applied to marine structures, chemical plants, susceptible to be damaged such as pitting, crevice corrosion. Crack initiation at corrosion sites. Material type number 3 is, aluminum alloys. Typically applied to marine, aerospace, transportation, susceptible to be damaged such as pitting, intergranular corrosion, fatigue cracks initiated at pits. Material type number 4 is, titanium alloys. Typically applied to marine, aerospace, chemical processing, susceptible to be damaged such as localized corrosion under certain conditions, fatigue failure at corrosion sites. Material type number 5 is, nickel alloys, typically applied to turbines, chemical reactors, susceptible to be damaged such as corrosion fatigue at high temperatures and aggressive environments. Materials most vulnerable to corrosion fatigue are those that combine susceptibility to corrosion, due to microstructure, composition, or environment, susceptibility to fatigue, high cyclic stresses, residual stresses, commonly affected materials include carbon steels, stainless steels, aluminum alloys, titanium alloys, nickel-based superalloys, and certain non-ferrous metals. Localized corrosion forms, pitting, crevice corrosion, intergranular corrosion, are especially problematic, because they serve as crack initiation sites, dramatically reducing fatigue life. Corrosion fatigue critical factors based on API 571, number A, the critical factors are the material, corrosive environment, cyclic stresses and stress razors. Number B, cracking is more likely to occur in environments that promote pitting or localized corrosion under cyclic stress due to thermal stress, vibration or differential expansion. Number C, contrary to a pure mechanical fatigue, there is no fatigue limit load in corrosion-assisted fatigue. Corrosion promotes failure at a lower stress and number of cycles than the material's normal endurance limit in the absence of corrosion and often results in propagation of multiple parallel cracks. Number D, crack initiation sites include concentrators such as pits, notches, surface defects, changes in section or fillet welds. Here's a detailed explanation of critical factors of corrosion fatigue damage. Corrosion fatigue is a complex failure process influenced by multiple interacting factors. Understanding these factors is essential for predicting, preventing, and mitigating damage in engineering components exposed to cyclic stresses in corrosive environments. Critical factors of corrosion fatigue damage. Number 1 is environmental conditions. Number A, type of corrosive environment, aggressiveness. The presence of chlorides, acids, or other corrosive agents accelerates material degradation. Temperature. Elevated temperatures increase corrosion reaction rates and affect material strength and ductility. Humidity and moisture. Higher humidity levels promote surface corrosion and pitting. Environmental conditions. Number B is chemical composition. Specific ions or chemicals can cause localized corrosion, pitting, crevice corrosion, which is more damaging than uniform corrosion. For example, chloride ions are highly aggressive in promoting pitting in stainless steels and aluminum alloys. Environmental conditions. Number C is flow conditions. Turbulent flow or fluid movement can remove protective oxide layers, exposing fresh metal surfaces to corrosion. Conversely, stagnant conditions may promote crevice corrosion. Critical factors of corrosion fatigue damage. Number 2 is mechanical loading parameters. Number A, stress range. The difference between maximum and minimum cyclic stresses influences crack initiation and growth. Higher stress ranges lead to faster crack growth and reduced fatigue life. Number B, stress concentration. Notches, welds, surface flaws, and geometric discontinuities amplify local stresses. These sites are preferential locations for crack initiation, especially under corrosive attack. Number C of mechanical loading parameters is loading frequency. Low frequency, more time per cycle for corrosion processes to occur, increasing damage. High frequency, less time per cycle for corrosion to act, but the combined effect may still be significant. and number D of mechanical loading parameters is type of loading. Tension, bending, torsion, or combined stresses influence crack propagation modes. Critical factors of corrosion fatigue damage. Number 3 is material properties. Number A, microstructure, grain size, phase distribution, and inclusion content affect crack initiation sites and pathways. Fine-grained microstructures generally improve resistance but may be vulnerable at microstructural defects. Number B, corrosion resistance. Alloys with built-in corrosion resistance, for example stainless steels, titanium, are less susceptible, but still vulnerable under severe conditions. Critical factors of corrosion fatigue damage. Number 3 is material properties. Number C, residual stresses, induced by welding, forming, or machining processes. Residual tensile stresses promote crack initiation and propagation. Material properties. Number D, hardness and ductility. Harder materials may resist crack growth but could be more brittle and prone to sudden failure. Ductile materials can absorb more energy but may still fail under localized corrosion attack. Critical factors of corrosion fatigue damage. Number 4 is surface condition. Number A, surface finish. Rough or damaged surfaces harbor corrosion pits and stress concentrators. Polished or coated surfaces reduce initiation sites. Number B, presence of coatings. Protective coatings can prevent environmental contact but may degrade over time, exposing the substrate. Surface condition. Number C, pre-existing flaws, microcracks, inclusions, or corrosion pits act as crack initiation sites under cyclic stresses. Critical factors of corrosion fatigue damage. Number 5 is time and exposure duration. The duration of exposure to corrosive environments influences damage severity. Longer exposure allows more aggressive corrosion processes to develop and propagate cracks. Critical factors of corrosion fatigue damage. Number 6 is temperature. Elevated temperatures accelerate both corrosion reactions and material deformation processes. High temperatures may alter microstructure or weaken passive films. Increasing susceptibility. Critical factors of corrosion fatigue damage. Number 7 is synergistic interactions. The interaction of the above factors often produces a synergistic effect, where combined influences result in damage greater than the sum of individual effects. For example, high residual tensile stresses combined with a corrosive environment significantly expedite crack initiation and growth. The critical factors influencing corrosion fatigue damage are interconnected and collectively determine the susceptibility, initiation, and propagation of cracks leading to failure. Effective mitigation relies on understanding and controlling these factors through material selection, design optimization, environmental control, and maintenance practices. Corrosion fatigue damage affected units or equipment based on API 571, rotating equipment, durators and cycling boilers, as well as any equipment subjected to cyclic stresses in a corrosive environment. Some examples include, Number A, rotating equipment. Galvanic couples between the impeller and the pump shaft or other corrosion mechanisms may result in a pitting problem on the shaft. The pitting can act as a stress concentrator or stress riser to promote cracking. Most cracking is transgranular with little branching. Number B, durators. In the late 1980s, durators in the pulp and paper, refining and petrochemical and fossil-fueled utility industries had major durator cracking problems. Complete vessel failures in the pulp and paper industry resulted in a diligent inspection program that found major cracking problems across the various industries. It was concluded that residual welding and fabrication stresses, stress risers, attachments and weld reinforcement, and the normal durator environment could produce multiple corrosion fatigue cracking problems. Number C, cycling boilers. A cycling boiler may see several hundred cold starts over its useful life which, because of differential expansion, continually cracks the protective magnetite scale, allowing corrosion to continue. Here is a detailed explanation of units or equipment affected by corrosion fatigue damage. Corrosion fatigue can compromise a wide array of structural components and equipment across various industries. Its impact is particularly critical in environments where cyclic stresses and corrosive agents coexist. Understanding which units are vulnerable helps in designing, maintaining, and inspecting these systems effectively. Units and equipment affected by corrosion fatigue damage. Number 1 is aerospace industry. Number A, aircraft structures, includes, the first is fuselage frames and skin panels, subjected to cyclic aerodynamic loads, susceptible to pitting corrosion, especially in humid or saline environments. The second is wings and spars, experience repeated bending and torsion. Corrosion pits can initiate cracks leading to fatigue failure. The third of aircraft structure is landing gear, endures cyclic compressive and tensile loads. Exposure to de-icing salts accelerates corrosion fatigue. The fourth of aircraft structure is engine components, rotors, discs. High-stress cyclic loading at elevated temperatures, corrosive environments from fuel and combustion byproducts. Number B of unit or equipment from aerospace industry is helicopter rotor blades, subjected to cyclic stresses and environmental exposure, especially in marine environments. Number 2 of units and equipment affected by corrosion fatigue damage is maritime and offshore structures, includes, number A, ship hulls, continuous cyclic loading from waves, corrosive saltwater environment promotes pitting and cracking. Number B, offshore oil and gas platforms, structural steel components under cyclic wave and wind loads, exposure to saline, humid, and sometimes acidic conditions. Maritime and offshore structures equipment. Number C, propellers and shafts, subjected to repetitive stresses, corrosion pits can serve as crack initiation sites, leading to failure. Number 3 of units and equipment affected by corrosion fatigue damage is automotive and transportation, includes, number A, vehicle frames and chassis, cyclic loading from road vibrations, exposure to road salts and environmental moisture causes corrosion fatigue. Number B, railway tracks and components, repeated stresses from trains, corrosion and fatigue combine to cause cracks and failures. Automotive and transportation equipment. Number C, aircraft and train components, similar to aerospace, with emphasis on high-stress parts subject to environmental exposure. Number 4 of units and equipment affected by corrosion fatigue damage is power generation equipment, includes, number A, steam turbine blades and discs, high cyclic stresses at elevated temperatures, corrosive environments from steam and combustion gases. Number B, nuclear reactor components, piping, pressure vessels, and core components experience cyclic thermal and mechanical stresses. Corrosive coolant environments, water, boric acid solutions, contribute to damage. Power generation equipment. Number C, hydropower turbines, cyclic loading from water flow, corrosive water environments can induce fatigue cracks. Number 5 of units and equipment affected by corrosion fatigue damage is chemical and process industry equipment, includes, number A, reactors and pressure vessels, cyclic pressure and temperature variations, exposure to corrosive chemicals accelerates damage. Number B, piping systems, repeated pressure cycles, corrosive mediums cause localized corrosion and crack initiation. Chemical and process industry equipment. Number C, heat exchangers, cyclic thermal expansion and contraction, corrosive fluids lead to pitting and fatigue failure. Number 6 of units and equipment affected by corrosion fatigue damage is civil infrastructure, includes, number A, bridges and steel structures, repeated traffic loads, exposure to de-icing salts and pollution causes corrosion fatigue. Number B, dam gates and penstocks, cyclic loading from water pressure, corrosion in water-rich environments enhances crack development. Number 7 of units and equipment affected by corrosion fatigue damage is medical and precision equipment, includes, number A, implants and prosthetics, cyclic loading during use, possible corrosion in body fluids leading to fatigue failure. Number B, precision instruments, exposure to humid environments causing corrosion fatigue over time. Corrosion fatigue can affect virtually any unit or equipment subjected to cyclic stresses in a corrosive environment. Critical areas include, structural components of aircraft, ships, and bridges, mechanical parts like turbines, propellers, and gears, pipelines, pressure vessels, and heat exchangers, civil infrastructure components exposed to environmental conditions, specialized equipment in chemical, power, and medical sectors. Mitigation strategies include selecting corrosion-resistant materials, applying protective coatings, designing to minimize stress concentrations, and implementing regular inspection programs. Appearance or morphology of corrosion fatigue damage based on API 571, Number A, the fatigue fracture is brittle and the cracks are most often transgranular, as in stress corrosion cracking, but not branched, and often results in propagation of multiple parallel cracks. Number B, fatigue cracking will be evidenced by very little plastic deformation except that final fracture may occur by mechanical overload accompanied by plastic deformation. Number C, in cycling boilers, the damage usually appears first on the water side of buckstay, structural, attachments, see Figure 4-141 corrosion fatigue failure of a boiler tube. The cracking pattern may be circular cracks surrounding the weld between the buckstay attachment and the waterwall tube. In cross-section, the cracks tend to be bulbous with numerous lobes. See Figure 4-142, metallographic mount of sample taken from failed boiler tube in Figure 4-141. The crack tips themselves may be somewhat blunted but are oxide-filled and transgranular. See Figure 4-143, higher magnification view of sample shown in Figure 142. See Figure 4-144, photograph of a carbon steel boiler tube cut in half lengthwise. Corrosion fatigue cracks initiate at the ID of a tube, opposite a buckstay attachment on the OD, Mag, 1X. See Figure 4-145, photomicrograph showing the crack morphology that is rounded with multiple lobes, and may branch to form rabbit ears. Mag, 25X, etched. Number D, in sulfidizing environments, cracks will have a similar appearance but will be filled with a sulfide scale. Number E, in rotating equipment, most cracking is transgranular with minimal branching. Here's a detailed explanation of the appearance or morphology of corrosion fatigue damage. Corrosion fatigue damage manifests in distinct surface and subsurface features that result from the combined effects of cyclic stresses and corrosive environments. Recognizing these features is essential for diagnosing failure modes and implementing preventative measures. Here's a few appearance and morphology of corrosion fatigue damage, includes, number 1 is, general characteristics of corrosion fatigue damage, surface features, presence of cracks, pits, corrosion products, and roughness, subsurface features, internal crack initiation, propagation paths, and microstructural changes, fracture surface. Fractography reveals characteristic patterns indicative of fatigue and corrosion interactions. Number 2 of appearance and morphology of corrosion fatigue damage is surface morphology features, includes, number A, corrosion pits, description, localized, often hemispherical cavities caused by localized corrosion, pitting. Corrosion pits appearance, small to large cavities with sharp or rounded edges. Pits often serve as crack initiation sites, can be covered with corrosion products, rust, oxides. Significance of corrosion pits, initiation points for fatigue cracks, especially in aggressive environments. Number 2 of appearance and morphology of corrosion fatigue damage is surface morphology features, includes, number B, crack initiation sites, description, microcracks typically originate at corrosion pits, inclusions, or surface flaws. Crack initiation sites appearance, tiny, often circular or irregular cracks emerging from pits, may be difficult to detect without microscopic examination. Progression of crack initiation sites, microcracks grow under cyclic loads, eventually coalescing into macrocracks. Number 2 of appearance and morphology of corrosion fatigue damage is surface morphology features, includes, number C, corrosion products and deposits, description, accumulations of rust, oxides, or other corrosion products and deposits appearance, flaky, granular, or crusty deposits on the surface, can obscure underlying cracks or pits. Impact of corrosion products and deposits may promote further corrosion or crack propagation. Number D, surface roughness and striations, description, striations are fine, parallel lines on fracture surfaces indicating cyclic crack growth. Surface roughness and striations appearance, regular, rippled patterns near crack tips, increased roughness in areas of corrosion-related damage. Significance of surface roughness and striations, indicates fatigue crack growth mechanisms. Number 3 of appearance and morphology of corrosion fatigue damage is fracture surface morphology, includes, number A, fracture zones, includes, the first is crack initiation zone, usually near pits or corrosion sites, characterized by rough, granular appearance with corrosion residues. The second is crack propagation zone, features striations or beach marks indicating cyclic crack advancement. Often shows a transition from intergranular to transgranular fracture modes depending on environment and material. The final fracture zone, ductile or brittle appearance, fracture surface becomes smoother or shows dimpled features in ductile failures. Number B of fracture surface morphology is corrosion-related features, includes, the first is intergranular attack. Fracture surfaces show path along grain boundaries, often in corrosive environments. The second is transgranular fracture, cracks cut through grains, with characteristic cleavage facets. The third is mixed mode fracture, combination of intergranular and transgranular features. Number C of fracture surface morphology is microcracks and crack coalescence, includes, multiple microcracks often originate from pits or inclusions. Coalescence of microcracks leads to macrocrack formation, visible as rough, irregular fracture features. Number 4 of appearance and morphology of corrosion fatigue damage is subsurface damage features. Internal microcracks initiate beneath the surface at corrosion pits or inclusions. Crack growth path usually follows the microstructural features like grain boundaries or inclusions, accelerated by corrosive attack weakening the material. Number 5 of appearance and morphology of corrosion fatigue damage is visual recognition of corrosion fatigue morphology. Pitted surface with crack initiation sites, rough, granular fracture surface with striations, corrosion deposits or rust layers, presence of intergranular or transgranular features depending on the material and environment. Corrosion fatigue damage presents with distinct surface and subsurface features. Corrosion fatigue damage presents in surface, corrosion pits acting as crack initiation sites, crack initiation zones near pits or flaws, fracture surfaces showing striations, beach marks, and corrosion deposits. Corrosion fatigue damage presents in subsurface, microcracks originating within corrosion pits. Crack coalescence leading to macrocracks, internal corrosion-induced weakening. Recognizing these morphological features helps in diagnosing failure modes, understanding the progression of damage, and developing strategies for prevention. Corrosion fatigue damage prevention and mitigation based on API 571, Number A, for rotating equipment, modify the corrosive environment by using coatings and/or inhibitors. Minimize galvanic couple effects. Use more corrosion-resistant materials. Number B, for durators, proper feed water and condensate chemical control. Minimize residual welding and fabrication stresses through PWHT. Minimize weld reinforcement by grinding weld contours smooth. Number C, cycling boilers, start up slowly to minimize the differential expansion strains. Always start up with the chemistry of the boiler water under proper control. Here's a comprehensive and detailed explanation of prevention and mitigation strategies for corrosion fatigue damage. Corrosion fatigue combines the damaging effects of cyclic stress and corrosive environments, leading to crack initiation and propagation that can culminate in catastrophic failure. Preventing or mitigating such damage involves a multifaceted approach, integrating material selection, design strategies, environmental control, and maintenance practices. Here is a comprehensive, detailed explanation of prevention and mitigation of corrosion fatigue damage. Includes, number 1 is material selection, includes, number A, use of corrosion-resistant materials, includes, corrosion-resistant alloys, select materials such as stainless steels, nickel-based superalloys, titanium alloys, or corrosion-resistant composites, high-strength, low-carbon steels. Use steels with controlled carbon levels and added alloying elements to enhance resistance. Surface-modified materials, employ materials with surface treatments, for example nitriding, carboizing, to improve surface hardness and corrosion resistance. Number B of material selection is microstructural control, refined grain size, fine grains impede crack initiation and propagation, inclusions and defects management, minimize nonmetallic inclusions and impurities that act as crack initiation sites. Number 2 of prevention and mitigation of corrosion fatigue damage is protective coatings and surface treatments, includes, number A, coatings, paints, epoxies, and polymer coatings, provide a barrier against corrosive agents. Metallic coatings, such as galvanization, zinc coating, cadmium plating, or nickel plating, which protect underlying metal, ceramic and composite coatings for high temperature and aggressive environments. Number B of protective coatings and surface treatments is surface treatments. Anodizing creates a protective oxide layer. Passivation enhances corrosion resistance, especially in stainless steels. Shot peening induces residual compressive stresses on the surface, reducing crack initiation susceptibility. Number 3 of prevention and mitigation of corrosion fatigue damage is design modifications, includes, number A, stress reduction, reduce stress concentrations, avoid sharp corners, notches, and abrupt changes in cross-section, optimize load distribution, use smoother transitions and generous radii, control stress levels, designed to operate below fatigue limit thresholds where possible. Number B of design modifications is component geometry. Use of symmetrical profiles, minimizes uneven stress distribution, avoiding stress risers, properly designed welds, joints, and fasteners. Number C of design modifications is environmental isolation, sealants and barriers, prevent ingress of moisture and corrosive agents, drainage and ventilation, minimize water accumulation and stagnation. Number 4 of prevention and mitigation of corrosion fatigue damage is environmental control, includes, number A, control of corrosive agents, humidities and moisture, use dehumidification or environmental enclosures, chemical environment, reduce exposure to chlorides, acids, or other aggressive chemicals via filtration or chemical inhibitors. Number B, corrosion inhibitors, chemical additives, such as phosphate or chromate inhibitors in cooling water, corrosion-resistant coolants, use of inhibitors in fluids. Number 5 of prevention and mitigation of corrosion fatigue damage is operational practices, includes, number A, load management, limit cyclic stresses, avoid overstressing components during operation, fatigue life monitoring, use real-time stress monitoring and load history data. Number B, inspection and maintenance, regular inspection, visual, ultrasonic, radiographic, or eddy current inspections to detect early signs of corrosion or cracks. Non-destructive testing, NDT detects subsurface cracks before failure, timely repairs and replacement, remove or repair damaged components promptly. Number 6 of prevention and mitigation of corrosion fatigue damage is cathodic protection. Principle of cathodic protection, apply a cathodic current to the metal surface to prevent anodic, corrosive, reactions. Cathodic protection methods, sacrificial anodes, use of zinc, magnesium, or aluminum anodes, impressed current systems, external power source applies protective current. Number 7 of prevention and mitigation of corrosion fatigue damage is corrosion inhibitors and chemical treatments. Surface coatings with inhibitors, incorporate inhibitors into paints or coatings, inhibitor dosing, regular addition of corrosion inhibitors in cooling or process waters. Number 8 of prevention and mitigation of corrosion fatigue damage is advanced and innovative strategies, includes, number A, design for durability. Use of damage-tolerant design principles to tolerate some damage without catastrophic failure. Number B, nanotechnology and surface engineering, application of nanocoatings for enhanced corrosion resistance. Number C, environmental monitoring and automation. Use sensors to monitor environmental conditions and fatigue stresses, enabling proactive maintenance. Effective prevention and mitigation of corrosion fatigue involve an integrated approach combining material science, engineering design, environmental management, and maintenance protocols. Prevention begins at the design phase, emphasizing corrosion-resistant materials and stress optimization, and continues through operational practices and regular inspection. Implementing these measures significantly extends the service life of components, enhances safety, and reduces maintenance costs. Corrosion fatigue damage prevention and mitigation based on API 571, number A, for rotating equipment, UT and MT techniques can be used for crack detection. Number B, for derators, cracking is generally detected with WFMT inspection. Many of the cracks are very tight and difficult to detect. Number C, cycling boilers, the first sign of damage is usually a pinhole leak on the cold side of a waterwall tube at a buckstay attachment. Inspect highly stressed regions in the boiler by UT or EMATS techniques. Cracking may occur at the membranes in the highly stressed regions, particularly corners at buckstays. Here's a detailed explanation of inspection and monitoring methods used to detect corrosion fatigue damage. Detecting corrosion fatigue damage early is crucial to prevent catastrophic failure of components. Since corrosion fatigue involves both surface and subsurface crack initiation and growth, a combination of non-destructive testing, NDT, structural monitoring, and advanced sensor technologies are employed. Here's a detailed overview of inspection and monitoring methods for detecting corrosion fatigue damage. Number 1 is visual inspection. It is purposed to identify surface anomalies such as corrosion pits, cracks, discoloration, and surface roughness. Visual inspection methods: direct visual inspection, using magnifying glasses or borescopes for hard-to-reach areas; remote visual inspection, RVI, using cameras, videos, or robotic devices in confined or hazardous environments; inspections frequency, regular intervals based on operational conditions and previous findings. Visual inspection limitations is cannot detect subsurface cracks or internal corrosion. Number 2 of inspection and monitoring methods for detecting corrosion fatigue damage is ultrasonic testing or UT. Principle of UT is, it uses high-frequency sound waves to detect internal flaws and measure wall thickness. UT is applied to detect internal microcracks, corrosion thinning, and crack growth beneath the surface. Their two other UT methods are, pulse echo method, detects reflections from flaws or corrosion pits, and phased array ultrasonics, enables detailed imaging of flaw geometry. The advantages of UT includes, sensitive to subsurface features and accurate thickness measurements. Limitations of UT includes, requires skilled operators, and limited access or complex geometries can pose challenges. Number 3 of inspection and monitoring methods for detecting corrosion fatigue damage is radiographic testing, RT. Principle of RT is, it uses X-rays or gamma rays to produce images of internal structures. RT is applied to detect internal cracks, corrosion, and voids, and suitable for thick or complex components. The advantages of RT includes, provides detailed internal images, and good for weld inspections and internal flaws. Limitations of RT includes, safety precautions required, and costly and time-consuming. Number 4 of inspection and monitoring methods for detecting corrosion fatigue damage is eddy current testing, ECT. Principle of eddy current testing is, it uses electromagnetic induction to detect surface and near-surface flaws. Eddy current testing is applied to detect surface cracks, corrosion pits, and material thinning, and effective for conductive materials like metals. The advantages of eddy current testing includes, rapid and sensitive to small surface flaws, and portable equipment. Limitations of eddy current testing includes, limited penetration depth, and less effective on complex geometries. Number 5 of inspection and monitoring methods for detecting corrosion fatigue damage is magnetic particle inspection, MPI. Principle of magnetic particle inspection is, it magnetizes ferromagnetic materials. Surface and near-surface discontinuities disturb magnetic flux, attracting magnetic particles to flaw sites. Magnetic particle inspection is applied to detect surface cracks and cracks just below surface, and useful for ferromagnetic components. The advantages of magnetic particle inspection includes, quick and cost-effective, and sensitive to surface breaking cracks. Limitations of magnetic particle inspection includes, only applicable to ferromagnetic materials, and cannot detect subsurface flaws deep below the surface. Number 6 of inspection and monitoring methods for detecting corrosion fatigue damage is acoustic emission monitoring. Principle of acoustic emission monitoring is, it detects transient elastic waves generated by crack initiation and growth during service. Acoustic emission monitoring is applied, continuous real-time monitoring of active crack growth, and sensitive to microcracking associated with fatigue. The advantages of acoustic emission monitoring includes, early detection of damage progression, and suitable for large or inaccessible structures. Limitations of acoustic emission monitoring includes, requires sophisticated data analysis, and noise from other sources can interfere. Number 7 of inspection and monitoring methods for detecting corrosion fatigue damage is fiber optic sensors and strain gauges. Purpose of fiber optic sensors and strain gauges is, it monitor real-time strain variations indicative of crack development. Fiber optic sensors and strain gauges is applied to embedded in structures during manufacturing or retrofitted. And detect localized strain changes due to crack growth or corrosion. The advantages of fiber optic sensors and strain gauges includes, high sensitivity and suitable for long-term monitoring. Limitations of fiber optic sensors and strain gauges includes, installation complexity and potential durability issues in harsh environments. Number 8 of inspection and monitoring methods for detecting corrosion fatigue damage is electrochemical monitoring techniques. Methods of electrochemical monitoring techniques are, corrosion potential measurements, detect changes in electrochemical potential indicating corrosion activity. Electrochemical impedance spectroscopy, EIS assess corrosion rates and surface condition. Electrochemical monitoring techniques application, identify active corrosion sites that could promote fatigue crack initiation. Number 9 of inspection and monitoring methods for detecting corrosion fatigue damage is advanced and emerging technologies, includes, infrared thermography, detects temperature variations caused by crack propagation or corrosion activity, ultra-fast and high-resolution imaging, laser-based techniques for detailed surface analysis, structural health monitoring, SHM, systems, integrate sensors for continuous monitoring of stress, strain, and corrosion parameters. Detecting corrosion fatigue damage effectively requires a multi-method approach tailored to the component's material, geometry, environment, and service conditions. Regular inspections combined with real-time monitoring systems enhance early detection, enabling timely maintenance or replacements to prevent failures. Thank you.